that's great. Right, so moving on then, as we've said, this session is going to be talking about something called the Magneto, and we'll go straight into it without any more preamble. This is going to draw on information that we've been talking about for the theory of the spark ignition engine. Okay, so piston engines, the spark ignition engine specifically. And earlier on when we've talked about this, we discussed the Otto cycle. And if you come down here, you see there is exactly what we've talked about with the Otto cycle. So sometimes known just simply as the four-stroke cycle. So you can see the induction stroke number 1, the compression stroke number 2, the ignition stroke number 3, and then the exhaust stroke number 4, typically characterised by the expression sub-squeeze bang plug. Okay. Every piston engine using a four-stroke cycle has those 4 strokes, but I'm specifically talking here about spark ignition engines where we need to get that mixture, a fuel-air mixture that comes into the engine during the introduction stroke to ignite, because what we're trying to do is convert chemical energy in the fuel-air mixture into mechanical energy, and then the mechanical energy is used to drive the machine, in our case, a propeller. Okay, so we are happy with that, and we move on. Now, if we notice, if we don't ignite the mixture, it's simple, the engine doesn't work. You just end up with puddles of chemical energy inside the engine, no mechanical engine. If we don't ignite effectively, you end up with a pilot that looks a bit like this. The rabbit of negative euphoria. Okay? So, because of that very simple, self-evident concept, we need an incredibly robust ignition mechanism for the internal combustion engine if it's going to be used in a, say, a life-critical application. Okay? And that's the pivotal part of this whole concept of using magneto in aviation. The ignition system we use must be ridiculously robust. It must have redundancy, it must have fail-safe modes or fail-line modes, as opposed to, oh, it's not working, no problem, we'll just pull over to the hard shoulder, hang on, I'm at 6,000 feet. Okay? So, how are we going to do that? Well, there's a number of things we can think about to say, ultimately, it's the magneto. Here, we can see the spark ignition engine, provides a spark that ignites, that's an ignition cylinder. And what components are we aware of that are in the ignition system? From what we've talked about before and what you know about, those who identify yourself as petrol heads, what's in an ignition system typically?
Spark plug.
Spark plugs, yeah, absolutely. For every cylinder, there's going to be at least one spark plug. And hey, that spark is where this spark that the ignition system produces is going to present itself. Anything else?
HT leads.
Yeah, HT leads, high tension leads, fancy name for the lead that takes the, what do I need to get the electricity to spark? What typically do I need? What sort of electricity?
High voltage.
High voltage, and that high voltage is characterised by the expression HT lead. Okay, so we need HT leads, we need spark plug, anything else?
Turning the key.
Yeah, we need an on switch, absolutely. We need some kind of ignition switch, absolutely perfect, yeah. And then we need some way of generating the spark itself. Now there's a lot of different ways we might do that. In aviation, for this spark ignition engine, that bit is what we're going to talk about in the magneto. But there are other ways of doing it. Okay, so yeah, absolutely. If we come down here, there's the spark plug, high tension leads, the ignition switch, and then the magneto. Okay, so absolutely, those are the bits and pieces that we have identified. Now, new engine designs don't necessarily work this way. Nerd moment. When did we stop using magnetos in cars? Ballpark. I'll settle for the nearest decade.
The teens.
Say again?
The teens.
The 1910s? The 1910s? Yeah, exactly. Around there. Okay, so basically, we haven't used a magneto in a typical car engine for road use for about 100 years. Yet we could pop down to the flight line and look in a Cessna 172, presto, there's a magneto. Are we just regressing? I mean, what is it about pilots? They want to hang on to this old technology. There's got to be a reason. Okay. So The reason is that the Magneto is capable of a couple of neat tricks that a car ignition system can only dream about. However, it also has some drawbacks, as some of you will find to your cost when you try and start any aviation engine with this type of ignition system on a cold and frosty morning. And I will be in here in the classroom, nice and warm, whilst you struggle out there in the cold and hopefully the wet, and I will laugh a lot. That's the problem with the Magneto. So conventional wisdom has said, okay, the Magneto is great, but maybe we can do other things. Maybe, for instance, we could go to a compression ignition engine, like a diesel engine in a car. And incidentally, you may or may not be aware, diesel fuel and jet fuel, basically the same stuff. So if you fit a diesel engine, suitably modified, into a piston-engined aeroplane, you can just shove jet fuel into it straight from the pump, no special fuel supplies required, and that will require some redesign in terms of the engine, but it also means no ignition system required at all, because it ignites on compression rather than having any electronics. But that's only been possible for about 15 years, because prior to that diesel engines were just too heavy. But now new material technology says we can get those diesel engines in. So we're looking at the end of the Magneto now in terms of general aviation, but it is, the fleet's still large enough that there will be, it'll be here for a long time. Okay, so we talked about this just before the start of the lesson and the ingredients for electricity. So one more time, just for me, we need to create electricity.
Magnet.
We need a magnetic field.
Copper wire.
We need some kind of conductive wire.
And movement.
And we need relative motion between the two. Okay? Because we are going to create electrical energy, and the laws of thermodynamics are quite clear on this subject. You can't get energy out unless you put energy in. So that relative motion between the two physical components is the energy going in. Okay? So exactly as you say, that's what we've got. Magnetic field, electrical conductor, turn it into a coil shape. That will make it much, much more efficient. Okay? You'll get a little bit of electricity if you go past one bit of wire, but if you go past 100 turns of the same piece of wire, you'll get more. Make it 1,000, you'll get even more, and so on. Okay. Right. Also recall, and again, we can't change this. The moment we have electric current going through a wire, there will also be a magnetic field, and that's vital in what we're about to discover. Okay, so that actually is a magneto. It's about the size of a fist. We can't see on the far side the kind of light grey bit. That's where the HT leads will plug into it. So however many cylinders the engine's got, 4 holes, 6 holes, whatever. And this bit on the front, that's where the kind of mechanical energy goes into it. In other words, this is where the energy to move the magnet that's inside there is going to drive it. So typically, via a suitable collection of rods, levers and linkages, that silver bit on the front is going to be connected ultimately to the crankshaft of the engine. Okay, so inside there we have a permanent magnet. Key point about this, the magneto is totally independent of any electrical system the aircraft has got. In fact, the aircraft may not even have an electrical system. You go back to a 1918 Sopwith Camel, there's no electrical system on there, there's no lights, no radio, nothing. It's got one of these and it works very well, thank you very much. Okay. That thing, no matter how much you drop it, kick it, abuse it, stick it outside in the rain, will quite happily generate brief zaps of about 20,000 watts. Okay, so how's it driven? Well, I've said that already, via the crankshaft, mechanical connection, no problem there. This often leads to a question. Anybody thinking of a question? Alison came up with one the last time I did this.
Can you adjust the timing of the...
Oh, absolutely. The timing is vital. That's not necessarily adjusted at this point, but you're absolutely right. We'll see in a diagram shortly that the ignition timing is a vital part of making this work. Yes.
How do you get the engine to tune so it generates current?
That's the question I was looking for. Yeah, absolutely. How If the magneto only works when the crankshaft turns, but the crankshaft won't turn until the spark is fired, and the spark won't fire until the magneto works, we've got a chicken and egg situation. Okay? And that's the most common question in this area. Alright, answer simple. Get out and push. Old style aeroplane, get some poor guy. You'll notice the officers in most air forces fly the aeroplanes, and the poor guys go outside. They have to stand in front of the big, arm chopper and swing it by hand, because that turns the crank, which turns the magneto, which enables the engine to start. Move on a couple of decades, maybe some nice engineer chappie will fit a battery and a motor to drive the crankshaft around briefly to get the crank to move so that the magneto can work. But once the engine is running, it doesn't need that battery anymore because the magneto is completely self-sustaining. But yeah, we need to get it moving. In a car, they did the whole, the whole crank on the front, or these days if we have to, maybe you have to push it. But, okay, right. So on that, why don't we use this system? Why don't we use the system anymore in cars? Well, because we found that this is a much more robust, reliable way of starting on a cold, frosty morning for a car. Put in a battery. Okay, we had to have one anyway to power that starter motor to get the engine running, and use the battery to drive something a little bit like the magneto. It's called an ignition coil, and that will produce the bulbs, and then the timing system, and then the sparks, etc. And that's terrific. It works extremely well. The problem with it, from a pilot's perspective, is this. That battery now represents, on this non-aviation ignition system, the battery represents a single point of failure. Pure and simple. Battery not there, ignition system no longer works. Battery goes flat because your generator or alternator has failed. Ignition system no longer works. This engine has now got multiple potential failure modes because it depends on the battery. The magneto doesn't have any of those problems, and that's why we're still using it 100 years after cars gave it a push. Okay, right, so aviation fundamentally wants to avoid single points of failure, and the battery became a single point of failure, so no, we don't do that. All right, now let's have a look. Because I told you why, but I haven't actually explained in any way at all yet how. So what I need to do is take what you've told me, and one of the things you told me was how we're going to create electricity. So let's have a look now. We said we needed a magnetic field, yeah? So okay, let's draw a battery. Magnet. There you go, there's a magnet. And by convention, North Pole in red, and there's a South Pole there. Okay? Now the battery's got to move, so we're going to put that battery on a spindle and we'll rotate it. Again, just a suitable collection of rods, levers and linkages, and that pivot just goes off to a crankshaft. No problem there at all. Okay. Next thing we needed, well, we've got two of our elements for electricity already, so what's the third thing we needed? We needed a coil, we needed the conductor. So there you go, let's put a coil there. So imagine this is just coils of wire, wound around some kind of non-conductive thing. For current to throw through a wire, you'll recall it's got to be a continuous circuit. So let's extend that wire over here to an earth point, and then over here, actually we're going to have three things here, so it's a little bit interesting. So we'll draw three things in there, and each of these also goes to earth. So although I've not drawn the wire going all the way around, what I want you to have in your mind is that that is connected to that, or that, thus making a complete piece of wire, and thus the current will flow through that wire. Okay? Marita, you said we needed an ignition switch, so there you go. Keep you happy, there's an ignition switch. Okay? Alright, in fact, I'm even calling that E, G, And this we're going to call our primary coil. Alright, so far we've kind of got the idea of creating electricity. And as a side effect of current flowing, what's the side effect again?
Magnetic field.
Magnetic field. So there we go, let's draw on a magnetic field. There it is. So those are lines of magnetic flux. Okay, there's a problem here. This would work. Everything that's happening here at the moment is absolutely solid, and that is now producing electricity. It's producing 10 volts, enough to light a small light bulb, provided you don't want to read at any great distance, but that's about it. Okay? So unfortunately, it's nowhere near the 20,000 that we needed. How could I maybe get a few more volts out of it? Thinking about again how we create electricity.
You were primary here, which requires signature.
Ah, that's true. You're way ahead of me, my friend. Hold that thought. I'll come back to you. Because what I was thinking was I could up the voltage by spinning this a bit faster. If I have more motion, then I get a bit more energy. But there's no way I can spin this fast enough to get it up to 20,000 volts. So that's not the answer. But the speed of the motion clearly does affect what we can get. Okay. So now, back to Michael's point, I've written primary coil, which is a little bit of a clue that there's going to be something else, and there is, it's a secondary coil. Now from electrics, what device might we use to change low voltage to high voltage? Transformer, absolutely. And what is a transformer? It's one side with a coil with a few turns, and another side with another coil with, well, if I want to go to higher voltage, more turns. So up here, we have a secondary coil. Now this one is going to have way more turns, thousands. I'm not going to do all. Okay? You get the idea. And again, that goes to somewhere. That goes to somewhere. Okay. So this is now our secondary coil. Alright, now the clever now. In theory, this electric field might have an effect on that secondary coil. The problem is, though, this magnetic field that we've got is not moving. Okay, it's a stationary magnetic field caused by a constant current flow. Remember, to get electricity, we needed the magnetic field, we needed the conductor, and we needed relative motion. But this magnetic field that I've drawn in orange is just static. I need to make it move. So how am I going to make it move? I hear you asking that. I'm going to do this. I'm going to put a clever little thing called a contact breaker here. And I'm going to put a rotating gizmo, which we will learn to call a cam. And as that rotates, it's going to open and close that contact breaker. Okay? When the contact breaker is closed, the circuit is complete, current flows, magnetic field is there. When the cam rotates and forces the contact breaker open, what's going to happen to the current flow? It's going to stop. And so when it stops, what will happen to the magnetic field? It will cease. It will collapse. And the way the physics works out, as that field collapses, it becomes a moving magnetic field. And you know what? Remember I said the faster the magnetic field moves, the more electricity you get? This field is going to collapse very quickly. And it's going to collapse quickly enough that at the moment of collapse, and it's a fraction of a second, you are going to get 20,000 volts off your secondary coil. For the briefest of moment. You mentioned ignition timing, that's why the ignition timing is vital. A fraction of a second before or after, there's nothing on the line, thank you very much. It's got to be exactly right. And that then leads us to suppose that if we put this wire down to maybe some kind of electrical connector with, I don't know, 4 potential outlets, 1, 2, 3, 4, then that is our distributor. That rotates. And as long as this connector gets to one of these 4 ports, volts at exactly the moment that that contact breaker is opening and the magnetic field is collapsing, 20,000 volts to that point. Okay, so that in essence is how we're going to get the voltage that we need. Okay, there's a couple of problems yet though. Whilst this is working, that's turning off and on, but I've also still got this ignition switch over here. So we need to think about that a little. Okay. What, just logically, looking at that switch, ignoring everything else I've said, how would you characterise that switch at the moment? Is it off or on? Off. Yeah, it's an open switch. Current can't flow. So, when I tell you that currently this ignition is on, that might surprise you. Don't you want to know why? Oh, yes, please. Thank you. Thank you, sir. Right, yeah, that ignition switch is currently, if we were to look at the key in the ignition, it would show this magneto as being on live. And this is why. If that ignition were in a closed position, if that switch was in a closed position, then when the contact breaker, which is on the same bit of wire, remember, closed, current would flow. So what? But when the contact breaker opened, current would still flow, which means the magnetic field wouldn't collapse, and if the magnetic field doesn't collapse, no relative motion, no 20,000 volts, no 20,000 volts, no engine. So, the system is designed purposefully that this ignition system has a failure mode which is fail live. If the ignition switch breaks, for instance, if there was a broken earth here, which due to all the vibration you get in these types of airplanes is quite a common fault, will the ignition still work? Yeah. How would the pilot know? Well, they wouldn't. Which is why pre-flight and post-flight you're expected to check the ignition magneto system carefully to look for any signs of a problem with that ignition switch. And why a very, very common question on this area is what happens if the earthing is broken on the ignition switch? Answer, when you try and turn the ignition off, the engine keeps running. Which actually doesn't matter because we always shut the engine down by killing the fuel rather than turning off the ignition on these types of engines. But the point is it's a fail live mode. Also, important point here, that means we always treat a propeller as live. Because if somebody has not spotted a broken earth lead by doing the appropriate post-flight checks and you lean on the propeller and it turns, hypothetically, the engine could start. It's one of those, like a lot of risk analysis, very small probability, but very, very literally high impact if it happened. So you always treat the ignition system as live regardless. Okay? So that's the ignition switch. And then finally, there's just this little character here. And this, again, we did mention in electrics, this is a capacitor. Okay? And the job of the capacitor is simply to protect the contact breaker here. The problem is, as this contact breaker is opening, in that first bit of opening, any current in here might just form a very, very tiny baby spark there, which would damage the surface of the contact breaker and over time would erode it. If we put a capacitor here, electricity, being the lazy SOB that it is, will go the easiest route, and its easier route, rather than trying to jump even a small gap, is to flow into the capacitor and wait until there's another way to go. Okay? So the capacitor here is simply to protect arcing across the contact breaker so it can function. Okay, but that, in essence, is, oh, sorry, I should have said, the cam here that drives the contact breaker, again mechanically connected to the crankshaft. So when the crankshaft is turning, that cam is turning, and bingo, that is the magneto. Okay. It can't fail, it's just, as I had a little note of there earlier on, basic physics. The only way you can really stop one of these working is to actually take it out of the airplane and hacksaw it in half. I've seen these literally in boxes for 20 years. Pull them out of the box, twist it, you can still get a spark. Okay. Very, very tough. so just to round off then, a bit of summary here. That's the same diagram that just on the board. And from that, to recap, what we've got are this magneto will generate sufficiently high voltage, somewhere in excess of 20,000 volts, to get a robust spark to jump across a spark. Next, it's completely independent of the aircraft electrical system. You could rip out every circuit breaker, bit of wire, light, the battery, everything. This magneto is still going to work and will still run the engine. The only thing you've done is maybe you have the hands with the propeller to get the engine started. Creates electric current as soon as the crankshaft begins to turn, cover that. Operates whenever the crankshaft is rotating. There's a bit of repetition there, I apologise. And then this fail-live design, which provides some fault tolerance. However, even though I kind of sold this as the brilliant never-fail system, well, okay, there's still a few things in it that might fail, like spark plugs, broken HDVs, things like that. So, the final bit of just cherry on the top, if you like, for the design, let's have two of them. Two magnetos, not one. So, we'll have duplication of the magnetos for redundancy, and the finished system then looks something like this. Where you can see this is a 4-cylinder engine looked at from above. One magneto to the left, another magneto to the right magneto. One ignition switch, and this is a standard convention for all spark ignition piston engine aircraft. The off position, yeah, we needed that. The right magneto, the left magneto, switch to that, and one magneto will be running. Clearly both of them running in the start position, just like the current car. Okay. Up here, you'll note each magneto powers one spark plug on each cylinder, thus giving each cylinder 2 spark plugs. Now you've got to remember, this isn't like a 1.5 litre Honda Civic engine. This thing is big. The pistons are that sort of size. So having 2 spark plugs in there gives you much more efficient ignition and makes the engine work better, and of course the other benefit of fault tolerance. The engine will still run on one spark plug, you just lose a little bit of your efficiency, a little bit of power. And indeed that's what we test. When I do my pre-flight, I go from both to the left and I look for a slight drop in RPM because I'm losing some of my chemical energy because I'm not getting such good combustion. Back to both, RPM comes back up. To the other one, RPM drops down again. Back to both, RPM comes back up. If you go from both to left and the RPM stays the same, you immediately think, well, if that magneto was actually working, and you investigate for that. Alright, so that is our final little bit. We can then just round off, throwing the floor open to you guys. Any questions? Yes, Mike.
So, you talked about the magneto and how fast that is. In this kind of system, is it distributed also earlier as well?
Again, duplicated by that. Like, one of the reasons you have the duplicated magneto system, because yes, wear in there or condensation in there, contaminants in there could cause that. But what we do find is that wear in a distributor or problems in a distributor would tend to make starting the engine more difficult rather than make the engine fail once it's up to temperature, etc. Okay, so A, we've got 2 distributors, one for each magneto, and 2, when distributors play out as the damps got in them, it's usually an engine starting problem rather than engine failing at 5,000 feet level.
So is it pretty much a case of you notice any kind of difference or lack of difference in RPM in the flight cycle, you really have to take it into account?
Absolutely, yes. If you, okay, so during the pre-flight, there's a set procedure. It varies a little bit from one aircraft to another, but you'll do what they call a dead check immediately after engine start, and that's when you're literally checking that if you turn the ignition to off, the engine starts to shut down because there's no sparks at all. That proves the earth is still connected, the ignition switch is still operational. Then you go to both, then you get to run up air once the engine's warmed up a little bit, and then you check each mag individually and check that the RPM drop was within tolerance. It's very simple, 250 RPM, something like that, or actually 150. But it will be in the aircraft flight manual for any given aircraft. So you're checking each individual mag is within tolerance, and also at that point you're checking the engine is smooth running. Okay, so the smooth running is making sure the spark plugs aren't fouled by rich mixture and that everything else in the system is providing as it should. Any indication of of rough running that you cannot clear with a couple of conventional techniques that are used, then it's okay, this is a bad day to go flying, let's go back to the ramp, shut it down, get one of the engineers to have a look at it. Any others?
This is the basics sort of Magneto. Are there different grades of Magneto?
Absolutely, yeah. Depending on the mission of the aircraft, and again, even the era of the aircraft. See, the thing is, if we go back to, let's say, the 1940s, and you look at something, everyone likes the Spitfire. The Spitfire was operating with a Magneto at 30,000 feet. Now, the problem is, at 30,000 feet, the air is very thin, and what you would get is arcing within the Magneto and the other parts of the electrical system because the air is so thin it doesn't insulate properly. So you have to pressurise the Magneto. But that's not something you need to do if you're only hanging around at 5,000 feet. So in the 40s and 50s, those last generations of really big, powerful piston engines and high altitude flight, the systems were much more sophisticated because they had to cope with a much more hostile environment. The moment people got the idea that actually the jet engine, the gas turbine engine, gives us a much better power to weight ratio and reduced complexity, once you've got the materials to make it, it's actually a less complex system. You don't make those big powerful piston engines anymore, and the Magneto therefore actually becomes a little bit simplified because it doesn't have to cope with so many different extreme conditions. But yeah, you go back to, say, the immediate post-war eras and you see some quite sophisticated stuff. Yes. Okay, that's great. Thanks, guys. We'll have a tea break now, and then we'll pick it up later